Thanks everyone for coming to the first of the new series of the ARMET Southeast Local Centre meetings. We're quite excited to start these again and hope we will be able to continue hosting them. And yeah, today, this month, we're going to be starting off with a PhD showcase, which we like to do every year. So in the department, all the second year PhD students once a year present their work. And these are judged by the staff, and then the winning students are invited to talk to a wider audience, and we're really grateful that they accepted. Thank you so much. And give 15-minute talks about their work, which is all incredibly interesting and very exciting. Few housekeeping things. Make sure that the slides work. If you need any first aid assistance, please let us know. John, you're a first aider. And we also have at the back there, and we also have the doctor staff on hand this evening. We don't have a final plan this evening. The meeting point is at the car park. And yeah, exit through this black door in front, back. We're going to redo all of the sign up requirements stuff at the end. If you are a student or staff or just interested, it's generally worth doing for access to funding, coming along to conferences, gives you discounts. But we'll put all these up at the end as well. If you don't already have access to journals, you get that as well. Different types of membership, but we'll skip through that and we'll probably go straight to a summary of the recent weather, which has been very kindly put together by our other Jake, who will be presenting to you. One other housekeeping thing I forgot to mention, we have a sign-in sheet. It's really great to know how many people come along to these. If we get good attendance, which we have this evening, which is great, that means we can keep this going and keep having more really interesting talks. We've got interesting things lined up for November and December. This will just help us be more comfortable inviting speakers from further afield for our 2026 events. We have a second sign-in sheet, which is just to gauge how far people have come for ARMET's carbon footprint statistics. So it'd be really great if you could sign in on both of those. So yeah, thanks very much everyone for coming, and I'm going to hand this over to Jake to run us through current weather.
Thank you. Cool. Hello, everyone. Hi, I'm the other Jake. I've had the pleasure of putting together the intro slides, as a tradition at these meetings. So, firstly, I'm going to take you through the weather in 2025 so far. So, if you cast your minds all the way back to winter, you'll remember it was wet. I remember being very miserable because it was cloudy all the time. And I was not deceived because we were 32% below average in sunshine hours. We were also slightly wetter than average as well, a theme which has carried on through 2024 and 2023. But this year, something changed. Spring, if you remember, was lovely. It was very sunny and very, very dry. It was also warm. So maximum temperatures were over 2.5 degrees above average, which is quite remarkable. Although the nights were still chilly, so 0.2 degrees or so below average under clear skies and with light winds. Very high pressure dominated month after a late sudden stratospheric warming, and there was plenty of blocking that persisted throughout the whole of spring. And rain, we were well below average, 63% less than average. Summer followed in a similar vein, very, very warm. No remarkable warm days, but consistently warm. So I think the maximum temperature at the observatory was around 32 degrees, so nothing exceptional, but it was consistently warm. So we ended up 2.5 degrees above average on the maximum temperatures and 1.75 degrees above average on the mean temperatures. And it was also very dry, very similar to spring. So how does 2025 so far compare to previous years? Well, it was definitely drier than previous years and much warmer as well. The last year we had more than 15% less rainfall than average was 2010, mainly because winter was very dry and most of the precipitation that fell was snow. So will we end 2025 with less rainfall than 2010? We'll have to wait and see. So this is a summary of what I just said. A wet start to the year. January and February had above average precipitation and then consistently drier than average all the way up until July, which had near average precipitation. Although this was mainly because there was a few days in there with very high precipitation amounts, mainly in the form of thundery showers. August was also very dry, and then September we actually ended with around average precipitation. But it was very front loaded. So we had lots of rain to start off with, and then a very dry second half. Sunshine much above average quite consistently throughout the year, apart from the start of the year when it was grey and miserable. Thank you. So because of that precipitation deficit through much of the year, we remain in drought conditions across many parts of the country. So I made these slides about a week ago, and definitely then much of northern England, the East and West Midlands were still in drought conditions according to the Environment Agency. So even with recent rainfall, we've not had enough to put the deficit that we accumulated through spring and summer. And you can see that summarized here. These are rainfall anomaly charts from the Met Office compared to the 1991 to 2020 average, so significantly below average nationwide in spring. Similar in summer, especially across southern and eastern parts of England. Thank you. Yeah, so I made these slides a week ago, and I started to notice it getting a bit chilly. This week it's now turned on its head, and it was very warm yesterday. It was over 20 degrees here at the observatory. And in northern and eastern Scotland, thanks to the Fern effect, it was well over 20 degrees. So this has changed. So we did have to spare a thought for Rob and his polytunnel and his veggies getting a bit of frostbite, but not anymore, it seems. Although we are going into a drier and more settled period next week, so we could have some chillier nights again. So across Europe, it wasn't just a hot and dry summer in the UK. It was very similar across Europe. So this is the cumulative area burned through wildfires up until the end of September. This grey shading is the max and min of the years between 2006 and 2024. And we've exceeded the area burned in that time period. So it's been the worst European fire season for more than 20 years. And that was mainly because of a late wave in Europe and lots of wildfires in Portugal and Spain. The total area burned is equivalent to 1.4 million football pitches, or 6.5 Greater Londons. So here's a picture of those fires. Some of them were city-sized in northern Portugal, the Rías Baixas region in northern Spain. And here you can see why. So after an already prolonged, hot, dry summer, we had a heat wave in August, where temperatures were consistently above 36 degrees in those fire-affected regions. And the anomalies were 6 or 7, 8 degrees above average. So 2025 globally has been another warm year, not quite as warm as 2023 and 2024. We started off with a record-breakingly warm January. Since then, it's got slightly cooler, mainly thanks to the ENSO region, turning into ENSO neutral or weak La Nina conditions. So this is the anomaly charts from a week ago. You see some nice Kelvin waves propagating across the equator, but elsewhere still very warm, especially in the North Pacific, the Arctic Oceans, which is keeping 2025 as being the third warmest year on record globally. So when I was making this, there was lots of ongoing tropical cyclones. Humberto here was forecast to head towards the UK and then later became Storm Amy. So I'll put this forecast up. This was the ECMWF forecast initialized on the 30th of September to see if it verified. And indeed, northern parts of Britain were experienced very strong winds and plenty of disruption because of Storm Amy. This is the forecast verification. So this is an analysis chart. And indeed, that forecast, that 3-day forecast was pretty good in the location of the strongest winds. Here's some facts about storm Amy. I'm not going to go into too much detail because I fear that someone else may be talking about the storm later. Okay, I'll go on. So we had the lowest surface pressure recorded in Shetland in October, 947.9 pascals. This time of year, a lot of trees still have leaves, so there was plenty of disruption to travel, and more than 100,000 without power due to tree fall. Northern Ireland saw its provisionally strongest wind gust at McGilligan, 92 miles per hour. A numerical weather prediction was struggling. This is a highly unpredictable event, tropical cyclone recurvature into the mid-latitudes. But at lead times around 96 hours or slightly greater, there were some ensemble members that were predicting the outcome that eventually unfolded. So there was plenty of time for the Met Office to issue amber weather warnings for northern parts of the country. Cool. So that's the intro done. And with that, I'd like you to invite me to welcome our first speaker, Nathaniel.
Cool. Good evening, everyone. I'm Nathaniel. I'm a third-year PhD student based here in Department of Geology here at the University of Reading. So yeah, I'm going to be talking a bit about some of my PhD work, calibrating probabilistic solar wind forecasts, and hopefully more broadly about how we can understand uncertainty in modeling, which can be more broadly applied to kind of climate and weather modeling approaches. So yeah, to begin with, what is the solar wind? So the solar wind is this kind of dramatic outflowing of plasma from the sun's atmosphere. So the outermost region of the sun's atmosphere is called the solar corona. It is of the order of several of millions of kelvins hot, and the vacuum of space is very cold. So literally, is this pressure-driven outflow. And this is a movie, a series of stacked satellite observations of the sun. And you can see in this animation here, there's a lot of structure, parts that are more dense, parts that are flowing out faster. And the structure in the solar wind is coming from the structure of the magnetic field embedded within the sun's atmosphere. And so you get this kind of highly structured outflowing mass of material from the sun, propagates out into the solar system, and it's the interaction with Earth's own magnetic field and this kind of outgoing flow of material from the sun, which creates what we experience on Earth as space weather. So the aurora borealis, the northern lights, this is an example of space weather. It's a pretty benign example of space weather. There are more serious impacts on things like satellite communication networks and kind of large-scale grounded infrastructure on Earth, things like national power grids, deep sea pipelines. So as we become increasingly reliant on those sorts of technology, it becomes more important for us to be able to forecast and model the solar wind properties as they arrive at Earth, namely how fast the solar wind is when it arrives at Earth, since how fast the solar wind is flowing is a loose proxy for how much energy it can transfer into the Earth system and how much hazard it might pose to Earth-based systems. So I'm just going to go on to talk about how we model the solar winds. Thank you very much. So yeah, I'm going to kind of go through this timeline structure where one end we have the sun, other end Earth, and we have various stages. So this is a coupled modeling approach. So we begin with maybe not.
Oh no, that's the sorry.
So we begin with observations of the magnetic field on the surface of the sun. So we use a combination of satellite and ground-based observatories, and we can observe the strength and polarity of the magnetic field on the surface of the sun, and you get this kind of gray image here. This is called a magnetogram. So black pixels are magnetic field going into the surface, white pixels are magnetic field coming out, and the color indicates the strength as well. And that forms the inner boundary for our model. We feed that to a corona model. This is kind of a numerical mathematical model which solves a horrible set of Maxwell's equations and gives us a broad reconstruction of the magnetic field in the sun's atmosphere. And as I said, it's the structure of this magnetic field which imparts structure into the solar wind. So you can relate the magnetic structure in this kind of 20 to 30 solar radii. It's like 10% of the distance between the sun and the Earth. is kind of the near sun domain. We can relate that structure to kind of broad solar wind parameters, things like density, temperature, and velocity, which is what we're interested in. And we feed that to what we call a heliospheric model. So this is a dynamical model or a hydrodynamical model, a magneto-hydrodynamical model, if you want to be fancy. And this is what propagates the bulk solar wind flow out into the solar system. So this animation here is something I pulled from the Huxt forecast. This is the operational solar wind forecast we run here at the University of Reading. And so, yeah, it propagates all those properties out into the solar system in this kind of characteristic. This structure is called the Parker spiral, and it relates kind of the broad magnetic structure of the sun's magnetic field out to the solar system. And so, yeah, from that we can extract a time series of wind speeds at Earth. So yeah, we can go through this big coupled thing, and we get a forecast, and it's crap. So as you can see here, we have a forecast in red. I think it's red.
Yeah.
Yeah, excellent. And our observations in black here. And you can see the forecast is not doing that well at picking out the structure. So I've deliberately chosen quite a pessimistic example of a forecast. It usually does a bit better than this, but I've chosen this example because there's a lot of uncertainty in that whole setup of how we go about forecasting the solar wind. And so a lot of that uncertainty comes with the fact that their physics, which links this kind of near sun domain out into the solar system, is not well understood. So this is where we want to start using ensemble forecasting techniques to try and access some of that uncertainty. So an ensemble forecast is when you run your model many, many times over and you subtly adjust the initial conditions you've used to generate that model, and it gives you a set of model outputs, which in theory represent likely possible outcomes. So it gives you a probabilistic forecast rather than just a single, what we call deterministic forecast, when you just run a single forecast out. And so, yeah, we introduce perturbations here to sample the uncertainty for an ensemble of models. And that gives us something that looks a bit like this. So now, instead of just that single deterministic forecast, we have an ensemble with ensemble spread. So in theory, where the ensemble is more tightly bound, that is like a region of kind of low uncertainty. The ensemble is very confident. Where the ensemble spread is much wider, there's a lot more uncertainty, it's a lot less certain. So yeah, so we've kind of gone from just saying, right, tomorrow there's going to be some wind speed to tomorrow there might be a 60% chance of some wind speed. And the introduction of that kind of probability kind of impacts how we can interpret our forecast. So yeah, now we have an ensemble, there's many things we can do with it. This plot is just me showing you that kind of timeline of models, but in a different way. So that corona model output, this map right here, we project out onto a lat-long grid. So essentially it's just a map of the Earth, but it's the sun, and instead of landmass, it's velocity of the solar wind. So we're only actually interested in the solar wind that's going to impact the Earth. So we project Earth position onto the surface of the sun across the ecliptic plane. That's this blue dashed line here. And then we want to perturb that position to try and sample some of the uncertainty of some of these structures we see here. Like there's a kind of high speed structure here, and there's kind of lower speeds here. And so, yeah, we essentially rotate our whole model setup to try and access different parts of the model as a way of trying to sample some of this uncertainty. You don't really need to understand this plot. I've just kind of shown it just to show you a bit of like how we're doing by generating our ensemble forecast down here. As I said, like you get a probability out from this. You get a probability out from this forecast, but that probability is only meaningful if we've calibrated our ensemble. And so we can introduce perturbations here. The next obvious question is, how big should these perturbations be? So it turns out this is quite a good question to ask. You can essentially write a whole paper, which is what we did last year, trying to answer this question, because you want to make sure your ensemble is calibrated. So if your ensemble is saying there's a 6% chance, say you have 10 ensemble members and 6 of them are predicting some event happening, you'd in theory apply that a 60% probability of that event occurring. But that only makes sense if your ensemble's been calibrated. So ensemble calibration is this process of tuning your model inputs and outputs to bring the forecast probabilities in line with the true likelihood of that event occurring. Essentially, making sure it lines up with how much you observe that event occurring. So when you say an ensemble has a 6% chance of, an event has a 6% chance of occurring, that is something that is actually reflected in your observations. And to do that, we use something called a rank histogram. So this is a very intense plot. I'm going to like indulge in it and really explain it. So bear with me as I explain some statistics. Please, it's interesting, I swear. So yeah, we use something called a rank histogram. So an ensemble's rank is the number of ensemble members which are over predicting a given wind speed. So if I have 10 ensemble members, 7 of those ensemble members are over predicting an observation, we'd apply that ensemble would have a rank of 7. So if we evaluate the rank for every single time step of our forecast and then plot the distribution, we get a rank histogram. And the rank histogram is quite a powerful diagnostic tool we can use to unpick various behaviors within our ensemble spread and our ensemble distribution. And so on the left here, this is an example of a well-calibrated ensemble. So our observation sits quite comfortably within the maximum extent of our ensemble, evenly at all ranks. So essentially our observation can sit anywhere in the ensemble spread. And the kind of stats way of saying is the observation becomes indistinguishable from any given ensemble member. An ensemble member is likely to have captured the true, the initial conditions of that represented that observation. And so you get this nice flat rank histogram out. So that is a well-calibrated ensemble. If we're overestimating the amount of uncertainty in a boundary conditions, like over-perturbing our ensemble, we introduce too much variability and get this overspread ensemble, which is essentially hedging its bets all the time. It's always giving us like 50, 60, 40% probabilities. So you get this kind of bullshit rank histogram that's biased towards middling ranks. And it just means your ensemble is really indecisive. And then the reverse is true. If you're under predicting your uncertainties, assuming there's not enough uncertainty in your ensemble, you get this really tightly spread ensemble that's really confident, but really confidently wrong all the time. You get this big bias towards low and higher ranks. It gets kind of characteristic bullshit. And so finally, you can use the rank histogram to unpick systematic bias in our ensemble. So this is an example of a systematically over-biased ensemble. So all the ensemble members are consistently over-predicting your observation. You get this bias towards low ranks. So you can see the rank histogram is this really powerful diagnostic tool we can use to unpick the various behaviors in our ensemble distribution. And so the calibration method we developed in that paper is essentially tuning the spread of the input conditions that go into generating our ensemble to try and get the best rank histogram out. And in doing that, we can make our ensemble more reliable. And reliability means your ensemble is more trustworthy, and you can use it as a more effective decision-making tool. So yeah, that's kind of the main result from that bit of work there. I just want to move on and try and talk a bit about how adding uncertainty into our models can help improve our model accuracy. So this is a bit of a counterintuitive statement because essentially you're admitting that if you admit that you don't know, if you admit you don't know something, you get better at predicting that something. And that's a bit hard to get my head around, but I'm going to try and explain it with another terrifying plot. But again, bear with me, I'll explain it. So if you want to evaluate how well your forecast is doing, the easiest metric is error. So you have your forecast value, observed value, take the difference. The smaller that difference, in theory, the better your forecast is doing. So that makes sense when you have a deterministic forecast, just that single time series I showed earlier. It's not that intuitive when you have a distribution of ensemble members. How do you work out the distance between your distributed ensemble and one observation? So we can use something called the continuous ranked probability score. This is essentially a mean absolute error like statistic as applied to an ensemble distribution. And so what we can do is we take a single time step of our ensemble and plot the distribution of ensemble members. So I have 100 ensemble members here, and I plot the distribution. So it's velocity at the bottom and the number of ensemble members which predicted that velocity. And on that, I've also plotted observation in red, and in blue is the deterministic model as a point of comparison. And so if we convert this histogram into a probability distribution function, essentially just normalizing it, so instead of the number of ensemble members, it's the probability of that ensemble member. And then from that, you plot a cumulative distribution function. So essentially just sum all the probabilities left to right, and you get this curve. And all the points in this curve are the probability of that wind speed or lower. And then you do the same for your observation in red, but that just comes out as this kind of step function, because of course, after that, it's always going to be that or lower. And then you evaluate the trapped area between those two curves. If you're a mathematician, we integrate between these two curves. You get this metric, CRPS, which is in units of kilometers per second, which is the value we're forecasting. And as you can see, when we do the same for our deterministic model, the trapped area between those two actually just comes out to the difference in those two values, forecast error. So what the CRPS is measuring is an error-like statistic, but as applied to this distribution. And as you can see, it's actually lowering it. And that's because this is a calibrated ensemble. So any one of these ensemble members, because it's calibrated, is equally as likely as containing the true inner boundary conditions which generated that observation. So even though it's like the most numerous ensemble member is one closer to the deterministic model, the second, third most numerous ensemble member is something closer to the one we observed. And so it's actually adding in useful information content into your forecast and bringing the overall prediction closer to your observation. And just to show that that's not a fluke, if you evaluate that over a big case study and average your forecast behavior over lead time, you can see that the calibrated ensemble is consistently reducing this CRPS, this error metric, across all lead times by quite a significant amount. And I've plotted that same data, just like not averaged, just so you can see doubly that it's not a fluke. And you can see that, yeah, over 10 years of data, the model is consistently getting closer to the observation. So I think that's the last point I want to leave you on, that admitting that you don't know something is sometimes helpful. Yeah, I'll leave my conclusions. This work is kind of a loose summary of stuff I've got written up in a preprint. So if you're interested in reading a bit too much detail about this kind of work, you can follow this QR code here. Conclusions there, I won't read them out. So yeah, I'll leave it there. Thank you very much.
Yeah, well, I mean, I thought that was amazingly well explained, but if anybody has any quick questions on that, we've probably got a couple of minutes for each questions.
Well, can you do the same sort of thing if you're thinking about predicting El Nino and things like that? Is it the same sort of thing, or would that work?
Well, I'm not a meteorologist, so
Is it a similar sort of thing?
yeah, well, so a lot of these methods we've kind of adapted from kind of meteorological methods. It's the difference in these methods comes a bit more in that all of the uncertainty in our modeling approach is in those inner boundary conditions used to generate our model. Because at the end of the day, we have one observation that's driving that whole forecast. It's that one observation of the sun's magnetic fields, and from that we extrapolate whether or not kind of the ensemble methods you use in kind of meteorological contexts, where you kind of there's chaos and turbulence you have to consider. Because the solar wind is turbulent, but we don't know how and on what scales it has an impact on. It's just the uncertainties are so much larger. It's just so much more noises that it's hard to link the two regimes quite easily. Yeah, thank you very much.
Right, yeah, thank you so much.
Right. Hello. So I'm Rhiannon. So my PhD work is looking at variability in the storm tracks, with a focus on the North Atlantic storm track, and a particular focus on the role of moisture and latent heating in behavior in the storm tracks.
Oh, they have a thing you can make it up.
May have to make either.
Wait, try again. Yes.
There we go. So as Jake alluded to, someone will be talking about Storm Amy, but it is going to be very brief. So you'll all, I'm sure, be familiar with mid-latitude cyclones. So this is Storm Amy that we had over the weekend. Thankfully, has done a lot of job of explaining the kind of impacts of mid-latitude cyclones forming, because I'm sure you remember last weekend. So mid-latitude cyclones are kind of one of the dominant drivers of kind of winter weather in the mid-latitudes. And yeah, they have very significant impacts. So understanding the kind of conditions that lead to the formation of these cyclones is really important. Obviously, Storm Amy, not exactly the best example of this because it was kind of an ex-tropical cyclone, but it's the first of the season, so I only have one to pick from. So if we're looking at mid-latitude cyclones and where they form, we're really focusing on the storm tracks. So I'll just introduce these. Yeah, these are kind of really where we get cyclones developing and propagating in the mid-latitudes. So the storm tracks feature, color doesn't show up that well. In the storm tracks, we get really strong horizontal temperature gradients. So you'll see here, we have kind of the dark color being cold air and the lighter color being warm air. And so in the storm track, we have, these very strong temperature gradients where we have warm and cold air very close together, and this allows us to create mid-latitude cyclones. The reason for this is where we have warm and cold air very close together, this is kind of physically unstable. We want that warm and cold air to spread further apart. And so this creates a cyclone to redistribute those horizontal temperature gradients. So we can kind of characterize where cyclones form and propagate with meridional heat flux. So that's here in these white contours. And so you can see that cyclones will form in this kind of area, and then they propagate up northeast. And so this is meridional heat flux is basically then advecting cold air to the south and warm air to the north. And this is then spreading those horizontal temperature gradients further apart. And so when we're looking at the formation of storms and storm tracks, we're really interested in barochronicity. So storms form where we have these areas of high barochronicity, and barochronicity itself forms where we have these strong horizontal temperature gradients. So these are just the colors from the previous plot. And you'll see that where we have a high area of barochronicity, that's because we have really strong horizontal temperature gradients. So barochronicity acts kind of like fuel for mid-latitude cyclones. Where we have a pool of barochronicity, these cyclones are able to develop and grow, and then as they do, they diminish that fuel, that barochronicity. And so here again is the meridional heat flux. So this is again how we characterize the behavior of cyclones, and you can see how it lines up with our kind of area where we have high barochronicity and strong temperature gradients. So we can quantify the relationship between barochronicity and heat flux with what we call the Ambaugh-Novak oscillator. So if we start with this plot on the left, there are a couple of ways to think about this. I personally prefer this left-hand plot. So this is a phase diagram where we have heat flux along the bottom. So this is our kind of storm activity. And as we move further to the right, we have more active cyclones. They're stronger, they have higher heat flux. And then barochronicity is on the y-axis. So as we move further up the y-axis, we essentially have more fuel in the storm track. We're able to develop more cyclones. So if we begin in the bottom left, this is where we have low heat flux and low barochronicity. So we don't have any cyclones in the storm track, but we also don't have any barochronicity. So we're not able to develop any more cyclones. But because we have an absence of these cyclones kind of redistributing heat, we're able to build up barochronicity. So we go up the y-axis clockwise, we reach a maxima of barochronicity, but at this stage we still haven't had cyclones developing. So we have a big pool of barochronicity. And now since we have this fuel in the storm track, we move clockwise to the right. As cyclones are able to develop, they increase heat flux. And then as they do, they decrease barochronicity. So this is basically as cyclones are developing and growing in intensity, they decrease barochronicity. Then we reach a maximum when we have very high heat flux. We have very active cyclones, but this has diminished barochronicity quite a lot. So you'll see we're kind of from a peak of like 1.4 per day, we're down quite significantly. And then now that we have less fuel in the storm track, less barochronicity, our heat flux decreases because we're less able to develop new cyclones, and we come back around to our area where we have low heat flux and low barochronicity. And another way to view this is with this kind of composite plot. So you can see in the green we have heat flux, and in the grey we have barochronicity. So we begin with high barochronicity, and then as heat flux is able to increase, we're able to generate a cyclone because we have this fuel for them. They increase, barochronicity decreases. As barochronicity reaches a minima and heat flux reaches a maxima, we're not able to develop new cyclones. So our heat flux decreases, and as it does, we're able to generate more barochronicity, which is this last step. And it doesn't quite recover to the point that it was initially. It takes some time for barochronicity in the storm track to recover to a point where we're able to generate intense cyclones again. And this is kind of what I'm interested in. I'm interested in figuring out exactly how barochronicity is restored in the storm tracks. So to understand baroclinicity, we should be able to calculate it. So the way that people typically calculate baroclinicity is with this ED growth rate. So this is dependent on zonal wind shear. So essentially where we have a strong difference in wind speed between low levels and high levels, we're able to generate cyclones because we have this baroclinicity. The reason for this is where we have strong horizontal temperature gradients, as we do in the storm tracks, this creates strong zonal wind shear, so strong difference in wind speed between low levels and upper levels. If we go to the original model where this equation is derived from, we can instead derive a slightly different form of it. So this is dependent on meridional entropy gradients instead. So where we're using entropy here, S, that's calculated with the logarithm of temperature. So it's essentially horizontal temperature gradients here. And so the difference here is that now we're calculating baroclinicity directly based on these horizontal temperature gradients. And you'll see there's these two equations have very similar distributions and magnitudes. The differences are essentially due to the real atmosphere not behaving quite like the model, so they don't quite match our assumptions. But both of these are equally valid ways of calculating baroclinicity. So now we have our kind of entropy framework. We have this new equation for baroclinicity. And what this means is that we can find an increase in baroclinicity in the storm track if entropy to the north decreases or entropy to the south increases. So this is essentially saying if we have a cooling to the north of the storm track or a warming to the south of the storm track, we'll have an increase in baroclinicity. And the opposite is also true. What we really find is that the variability in entropy to the north of the storm track is much, much stronger than variability to the south. So here we have ERA5 data of the box that I showed, and then 50 north. So this is specific entropy for, so across, so here's our north line, here's our south line. So this is specific entropy along the north every year in the faint lines, and then a median in bold, and then the same for the south. And so we really find that variability in baroclinicity is dominated by variability in entropy at the north. The south is really contributing noise to the signal and little else. So this points to a couple of possibilities in how baroclinicity is enhanced. It kind of suggests more of a dynamic perspective where we have coolings to the north rather than warmings to the south, kind of impacting baroclinicity in the storm tracks. So we can then go a step further from just this entropy gradient equation. We can instead consider baroclinicity first, only where the north is varying. So here, everything in our, there is a C up here, but that's fine. If anyone particularly, there you go, there it is. Yeah, so first of all, we have on the left, this is our kind of a reconstructed version of baroclinicity, where the only thing that's varying, the only varying parameter is entropy along this north border. And what we find is that it captures 90% of the variability in baroclinicity in the storm track, which I think is really quite, you know, I don't want to say impressive, but the fact that instead of looking at these small scale details within the storm track, you know, people previously were looking at 2 pressure levels or more potentially in this whole region to calculate baroclinicity. Instead, for this area, to calculate mean baroclinicity in the whole area, we just have to look at 1 pressure level with 1 line of temperatures, essentially. So that's for the north on the left. We can do the same for the south, just to make sure that this isn't a fluke. And you can see that it's much worse at approximating baroclinicity. So what we want essentially, if this was a perfect metric, we would have just an exact 1-1 line. So there is of course spread in our version on the left, but yeah, I'm sure you will agree. Looking at the north makes more sense than looking at the south when you consider the variability in these. So yeah, I do want to hang on to this just another second because again, I'm just very surprised that all of the detail and barachronicity in storm tracks you can capture by just looking at the north, essentially. So this agrees with the idea that kind of the behavior in the storm tracks is very much controlled by processes that happen to the north. So possible things like cold air outbreaks, where you have cold air from North America moving south towards the storm track. This will cool that north border significantly, and that could lead to an enhancement in barachronicity. So kind of this allows us to do a couple of things. One of them is to consider the sources and sinks of entropy, which is easier than considering, say, sources and sinks of zonal wind shear. So we now have barachronicity for the whole storm track region just in terms of entropy at a single line of latitude. We can look at the different processes that increase and decrease that entropy. And so this is an entropy budget that I've constructed. So these are all kind of source and sink terms on the left, and this gives us a residual moisture term on the right. One of the reasons for doing this, there's a lot of contemporary research looking at how moisture impacts barachronicity and then how this contributes to the growth of cyclones in the storm track. So people tend to think that as you have increased latent heating, so for example, if you have air moving vertically up, vapor in that air will condense, release energy. This could lead to an increase in barachronicity. What we actually find is that if you increase this residual moisture term on the right, so if you increase latent heating, actually what you'll be doing is this corresponds to an increase in dsdt, which is kind of the rate of growth of entropy. What that means is that you're actually, if you think of barachronicity increasing as entropy to the north of the storm track decreases, latent heating will actually decrease mean barachronicity in the storm track. And this is different to a lot of other findings. So a lot of people are looking at small scale processes, so latent heating very local to cyclones, and saying that this leads to secondary cyclogenesis and increases barachronicity local to the cyclones, and then you have further cyclones developing. Whereas this looks like actually latent heating heats that north side, and then because you have a weaker gradient in temperature between the north and south sides of the storm track, you actually decrease barachronicity in the storm track. So this lets us so we're doing a lot of analysis looking at the different sources of sinks and entropy. It's not quite in a position where I want to present it because there are a lot of very ugly plots that I'm not going to make you go through. But yeah, I'll just conclude now. So as I'm sure you're aware, the storm tracks are kind of a major contributor to winter weather in the mid-latitudes. Hope if you weren't aware before, barachronicity is kind of like the fuel that we use to look at these storms. And we can approximate barachronicity by just looking at entropy to the north of the storm track. Really suggests that a lot of the fine scale structure in processes within the storm track don't really contribute to a growth in mean barachronicity within the storm track, which is really what we're interested in. Because when you think of the development of cyclones as kind of from Rossby waves, it's really these large scale processes that you're interested in rather than smaller scale increases in barachronicity. And so then, again, looking forwards, maybe looking into the effects that latent heating have, and maybe it's not quite as clear cut as some people currently are suggesting that latent heating increases barachronicity. There might be more going on that we need to look into. Thank you very much. Yeah, any questions?
Time for one quick question on religion, Judith, so yeah, please ask you.
What is the effect of climate change on bioenergy? Is it increasing or decreasing?
It's difficult to say. So to a kind of zeroth order approximation, I would say so we have this biochronicity being proportional to the kind of difference in temperature between the north and south. If you had uniform heating, then the difference wouldn't actually increase or decrease. So that would biochronicity wouldn't change in that sense. Realistically, I don't know what. So Arctic amplification is kind of being discussed a lot with climate change. If you had the North Pole warming, that is going to then decrease biochronicity in the storm tracks. And then we also have, of course, if we have increased water vapor in the atmosphere, that's going to have its own impacts. It's part of my project kind of is also looking at the effects of climate change on biochronicity. I think that I'm aware, storms will probably become less frequent, but they will be more intense, is my understanding. Yeah, so I couldn't exactly say, I couldn't put a concrete answer on it, yes or no. Thank you.
So much, all right. Is it going to be done?
I can get rid of it.
Yeah.
Hi, I'm Kuran, as Jacob said, and you've had a talk on space, you've had a talk on the atmosphere, and I'm going to give you a talk on the ground or on the rivers. And particularly, it's going to have physics and machine learning. I was a mathematician in a previous life, or 2 years ago, and I still am maybe, but I can do other things as well. And I want to talk to you a bit about that, hopefully in a non-scary way. Just to start with, what is river discharge prediction? Like, it's a term that's just really quite simple. It's how high or low the river is, right? So this is the River Kennet, like a few kilometers away. And over time, the river is going to go higher or lower, and we want to know. Why do we want to know? If you remember, sort of 2 years ago, it was raining quite a lot in the winter. Like, I think it was about over a month of non-stop rain, like every day it was raining. And so there were days I remember when I was cycling to like the climbing gym in Oxford Road, and the roads were just flooded. I couldn't cycle, but you see the car slightly rise. That's quite a problem. I remember my supervisor got stuck in traffic for like an hour or two, just because the roads weren't working. And this year, you've had quite a dry season. It's like the rivers are a bit lower, and that's causing some problems in terms of how much water we have available for various uses, like sanitation and just clean water and a lot of industry, right? Now, when we look at that, is these like hydrographs, it's called. Just over time, how fast is the water, how fast the water is going through a river is like a one-to-one mapping for that river and how much water is in there. We know how fast it is, we know the sort of shape of the river, we know how much water is in that river. And what you can see is the rivers are quite spiky, right? It's not just sort of doubling and halving slowly. You really get these huge jumps. In the blue lines, you see like intervals, these probabilistic forecasts that I've made in the model I'm working on right now. I'm showing you what it looks like, talking about the River Kennet, but there's just like a lot of rivers. And in some of those rivers, it matters a lot more. Some places flood a lot more. For example, in like Bangladesh is known to have a lot of floods that cause quite a lot of damage. Some places have a lot more drought. You might have farmland that like lives off of the rivers going through it, going near it. And so knowing how much water is going through that river is going to change decisions of different people. It might tell a farmer whether or not they can use all the water that's coming in right now for the crops, or if they need to save some for later. There's going to be a dry period. So in my PhD, I work on predicting river flow, river height, whatever you want to call it, but I work on it on like a global scale, not just for the River Kennet, for a bunch of places as well. And in particular, we do have a model that does this. It's by the Eastern WF, a few kilometers down the road. It's called GLOFAS. It's called GLOFAS. It's a global flood awareness system. And half of my supervisors are from Eastern WF and try and work, my goal for the PhD is to make an AI version that might be able to do some things or run a bit better than GLOFAS. There's been a lot of people doing that in hydrology. And from what I've gathered, there's also been a lot of people doing that in weather forecasting, right? We have GraphCast, we have the AIFS, the Eastern WF version. And so often when I've been around talks in the cafeteria, in the coffee area or elsewhere, it becomes a big conversation. During when GraphCast first came out, there were these discussions and people often pick these sides, right? We had sort of these physical models. In hydrology, this is something that captures sort of, we have a bucket for soil, a bucket for rocks, a bucket for the trees, a bucket for everything. And we sort of model it piece by piece. And we're going to go in and take physical measurements of how fast the water goes down. And we do everything physically. And we'd say in review weather forecasting, this is really important. We need the physics, we need to trust it. This is what we need. Then you'd have people, maybe like myself 2 years ago, who'd say, like, no, what we really need is great results and black box models, and AI can take over the world and it can do everything. We don't need any structure. All we need is loads and loads of GPUs and loads of data. And I think these two sides of people just hate each other a lot of the time. Because you have these conversations, like I've seen it a lot, and it would start with, have you seen GraphCast? It looks really cool. And then they'll say, yeah, but it's not doing this thing or it's not doing that thing. What we really need is these physical models. And then sometimes you'd have someone, or usually at the end of the conversation, someone would talk about this like golden goose, this like magic hybrid model. And for me, I think about that as a golden duck. And the reason that I told you half my supervisors from the Eastern WF, and they love ducks. They say that like when you go to the Eastern WF, they can't like put their hands in their pockets without a duck appearing. They put that one back. This is actually made by one of my friends at Eastern WF to talk about hybrid hydrology, this like middle ground. But like did more of my PhD, it's maybe a bit disingenuous. And we talk about it as if we have it's a great chasm, it's a great space between physical models and these black box models. But I think what I want to convince you of is actually a lot of things in between that, right? So the first most obvious thing is calibration. So this is a cumulative plot of scores. Don't need to worry too much about it. Just know that curves moving further to the left are better performing. They better predict river flow. This is by the Joint Research Council. And the black one is sort of GLOFAS, this global flood model without calibration. This yellow is the one with calibration. And there were certain levels in between. And what you can see is that calibrating, so that means is like tuning parameters of this physical model, not because we tested the soil and we saw that that's the value of the soil, but because we like played around with numbers and we saw that these numbers make the model run better, gives you about a doubling in performance. That's not a physical thing, that's a statistical thing, but we do it all the time in weather forecasting and in hydrology. Then from the other side, you might start off with a black box model, but more often we like choose the type of model that we use to make more sense physically. So in hydrology, we use these things called autoregressive models. All you need to know about them is they have time baked into the way that these models work. So it goes at every time step, it takes a summary of the previous time step, takes information from the current time step, and it combines those to make a prediction for the next time step. Unlike these forms of machine learning models, they don't tell you about time, tell you about some of these really important properties, Like in rivers, what happened yesterday really matters today, right? It's the same thing in like weather forecasting. The temperature of yesterday might give you a good guess of what's going to happen tomorrow. We can plug those in to machine learning models. They aren't just black boxes. Going back to the other side, we have post-processing and data assimilation. And I think many people, including myself, are frightened by post-processing and data assimilation. But it's very important, right? It changes our models. The reason we keep doing it, despite how scary it is because it matters and it helps our models. This is like Wynn. She's a PhD here. She recently passed a PhD, now she's working with AWS. This is before post-processing. CDFD is the model she's working on. This is after. Black line is the truth. And you can see that having this post-processing, which doesn't always ensure that physics is preserved, it mostly just focuses on getting a better score. It's trained to minimize an error score or to maximize a skill metric. These are non-physical things that we use all the time in the IFS. I'm pretty sure in the Met Office, I don't work with them. And it really matters in traditional hydrological forecasting and weather forecasting. I think it's all sick because I've got a dry mouth. On the other side, we can add physical loss functions to our machine learning models. That means, so like machine learning models, their only goal is reduce some error metric using this thing called gradient descent. Not very important right now. You can add to the error metric physical loss functions. You can punish it for disobeying stuff like the water balance equations. So you can force it to obey some physics. In an extreme version of that, we have a thing called emulators. If you remember Talking Tom back in the day, it was like the thing that would mimic your voice. And what emulators do in machine learning, hydrology, weather forecasting space is they're trained to just copy the output of the model. So that's the start of things like GraphCast, of things like this. The way that they began is it was just take the IFS, the like Eastern of the Earth weather forecasting system, and just predict without being to predict. You can do that a bunch of times. And the goal there isn't to make the perfect model. The goal there would be to get a really good starting place or get a model that behaves just like the physical model, but that is way faster to run. Again, that's another form, physical motivation of trying to make your machine learning models way more physical. Again, from the other side of the plate, we have differential modeling. It's a confusing topic. All that means is that you take your physical model and you make it look like a machine learning model. You allow yourself to do this thing called gradient descent. Allow it to be driven by these statistics and error metrics, a bit like calibration, but in a much deeper, much more machine learning way. And these things connect, right? So really what I'm trying to show you here is that this debate that we keep having isn't really a fair one because we're always somewhere in this middle, right? We're always this sort of, well, we have other things. We have variable transformations, we have feature selections. At all points in time, we are working on models that are somewhere between this type of like hybrid duck that I'm talking about. So how do I do that? I've shown you this thing. How do I do this in my PhD? The first time that I did it was for using machine learning models, with inspiration from machine learning to sort of change things. In machine learning, it's a really important fact that using more data and using more regions helps your model. This is untrue in traditional hydrology. In traditional hydrology, we train a model to a specific river, specific basin, specific area. We get really good at that basin or at that area. And that makes sense, right? We like tune ourselves to those specific niches. But in machine learning, what's really important is having a diverse range of samples, diverse range of conditions to learn from those. And you can see again, I mentioned before, moving to the right is better. This is a model trained on a region as opposed to a single location. That's a surprising result in hydrology, and we can use that here. And so that's what I did. My first model, the first paper that I wrote, had a split. What we did is we had the first part of the model learn globally, learn everywhere, learn as much as it can for as much data as it can. That's that machine learning intuition, right? We also had sort of a fine-tuning piece. Like, this was almost like a variable transform. or the first block part of the model. Give me the second part that would tune itself in the way that we have this tuning of those traditional hydrological models to get really good in a single area, single basin, catchment river, there are all these names for it. And that worked pretty well. That works better than doing either one in isolation. There's a paper on that, if you're interested. It's something I'm quite proud of. And that was using machine learning, right? Using the intuition that comes from machine learning to make a better model. But you can also go the other way around. I work on machine learning models. Sometimes it's important to use intuitions gained by hydrologists and meteorologists and these physical forecasters. For that, I was going to use rollout. So rollout is something we use all the time. And what it does is it makes a forecast, let's say 1 day in the future, and it uses that forecast to drive the model again to get a day 2 forecast. So in the IFS, you'll make forecasts of what's going to happen 1 day in the future. Okay, let's use those forecasts. Let's run them into the model as if they were an input and get a day 2. That doesn't really exist in machine learning. We don't often do it. We have that autoregressive thing I told you about before. All that really does is it summarizes what was happening on day 1 to feed day 2 in the future. And that summary doesn't necessarily mean that it treats its forecast for day 1 as fact, whereas rollout genuinely does. So that's what this model is about. I'm not going to go through these numbers. You don't need to know about it. All it does is making a probabilistic forecast for it. And that worked really well. In particular, what we were looking for is, does using this rollout approach mean that the actual curves between that 1 and 10 day, that time series of river flow, is that more realistic than if we just predicted each day independently, right? This is a rank histogram. Thankfully, Nathan has told you about that. And so you know that a flatter curve is better. The blue one is my model. The other ones are just benchmarks. You see that in all these measurements, like measuring the 10-day flow, we're saying 10 days ahead forecasting. It's flatter. Autoregression is like memory property of a river, whether or not it's really spiky or whether or not it's really smooth. That's modeled better by a rollout. Same with sort of this sort of raw spiking. How many times is the day after greater than the day before? This standardized variance score. How flashy is another way of doing this? And this physical intuition genuinely means that you can get better ensemble forecasts in your machine learning model. Those are the 2 things that I worked on. But again, that wasn't necessarily the point. The point was this, and how there's a lot of models. I don't think really any of them are all physical or all machine learning. Thank you.
Thank you so much, Graham. I understand with class 8, but does anyone have any questions about that? That was fantastic and well explained, just as the previous ones. No? All right then. Well, thanks again, Graham. So next month, we'll be having the meeting on the 4th of November, and they'll have Paul Knightley talking to us about Toro, a project that looks at tornadoes in the UK. I think he said he'd also talk about his experience with storm chasing and other things. This one was requested to us, I think, by some of our undergraduates. So I think it's a really interesting subject, and I hope you will too. If anybody wants, like, has an idea of someone they'd like to talk next year in 26, please feel free to send me an email or come find me in departments. Thanks so much to our speakers. I thought it was fantastic. You all presented super well. There's no one that you won the prize last year. I think that's all. I'm sure some people are going to be going to the pub.